boundary method for computer simulations of the cell growth and division.
Okay. Thank you for introduction. Okay, so let's take a break from tumor or cancer for a minute. Okay. This is the preliminary work for tumor tissue simulation. So this is just the normal cell growth and division. So the title is about the three-dimensional immersed boundary method for computer simulation of cell growth and division. And those are collaborators. And so I'm interested in the morphology evolutions. Okay, so the outside, the shape, not the inside yet. Okay, let's see. So the animal cell cycle, the parent cell has the is duplicate the DNA, and then it grow about twice from the original one, and then generate two daughter cells. Okay, so I want to simulate this. Okay, so first of all, we have to decide where is the cleavage locations. Okay, so we have to model that the decision of that cleavage location. Okay, so as I told you already, I'm interested in the morphology transition. Okay, so the outside shape. To model numerically, there are many kinds of methods, and there are two types. One is the interface tracking, the other one is interface capturing. In the interface tracking category, there's boundary integral method, or friend tracking, immersed boundary, and immersed interface. And there's the immersed interface capturing method is the level set, is very famous one, and phase field. Well, each method has its own advantages and disadvantages. For example, some have good for preserving mass, some for good for tracking the interfaces. So this one is interface and multi-component fluids, a short paper about the methods. And specifically for phase field models for multi-component fluid fluids, this is the recent review paper. And another comparison paper is about the level set and phase field immersed boundary for two-phase fluid fluids. Okay, so for interface tracking, so for example, you have the cell, the membrane. To track the cell membrane, we put the particles, and then we track the particles. And the other method is interface capturing. So instead tracking the interface, we define some scalar function. Well, in level set, so we have the signed distance function from the membrane, the distance. The inside is positive, and outside is negative, and we define the difference, the distance. Or we can define the order parameter. The inside is almost 1 and outside is almost 0. So we define the everywhere the scalar function, and then later we capture the interface by the level set. Okay. So in this case it's 1/2. So in time dependent the movement of the interface in interface tracking. So the interface is moved by the velocity. So we track each particles, the underlying velocity field. And for a scalar function, ideally we want just convection or advection equation. But numerically we got a problem because the interface is compressed or too relaxed. So there are some other terms to prevent that. Okay, so actually I'm the specialized is phase field, so I try to everything in the phase field model. For some cases, it have some limited. So I will explain what is the limitation. Well, eventually I want to do the tumor cell tissue. Okay, so it's the ensemble average of cells. Well, single cell is no problem. Okay, so let's see. If I use a level cell or phase field, like the interface capturing method, then what problem we have? So initially, the single cell is double the mass, and then it generates the daughter cell, and then the interface is too close. they merge again. Okay? So it's not physical. So that's why I choose the other muscle, interface tracking muscle. So that's the choice of the interface tracking, for example, the immersed boundary muscle, the reason why for this case. Okay. So this is the previous model using the immersed boundary muscle, but it was still 2-dimensional. But I'm not sure she moved to the 3D. So basically, the underlying the fluid is navier-Stokes, is governed by navier-Stokes, and with source term, so 2 acetone location, there is the fluid source. So then generate the mass. So it double the mass, the cell grow by the 2 source. And by the time it reached to the twice of the initial volume, okay, so this is 2 source term, and then we divide the half and find the 2 opposite points and connect to each other. So that make the contract ring, okay, the contracting force. Okay. So that is the previous model by the, I don't know how to say it, Lanier, okay. Okay, thanks. Okay, so but the previous model is how to simulate this cell bridge. It's a little bit wider because it's only 2 contracting force is attracting each other. So it's very it looks like the cusp shape. So how can we generalize this model? So we propose a new contracting force model. It's mathematically it's very simple. Okay. So this is the previous work using the axis symmetry. Okay, so usually when we calculate the 3D computation or simulation, it's very costly. Okay? So you have to wait a very long time. So there's one of choice is using the axis symmetry coordinate. It's 2-dimensional, but effectively it's 3D. Okay? So this is the axis of symmetry, and that is the radial direction. So that is 2 source term, and this is the cell membrane. Okay? From the cell membrane, we can find the distance and find the difference of 2 distance, and then the reciprocal. So we choose the force is reciprocal, which means the contracting force is the strong in the equator location and the smallest on the pole region. So this is illustrate of that contracting force. So these 2 points are the acetone locations, and then that is the equatorial position. We have very strong the contracting force. Okay. All right. So this published a couple of years ago using the immersed boundary muscle. But in that case, we have just a 1-dimensional immersed boundary. Because it's axis symmetry, we assume the axis symmetry, and we can find the 2 principal curvature very easily. And okay, so this is the model. Okay, so we have the cell grow, okay, 2 esters, and make the flow source, and then double, and then we activate the contraction ring. And this is the previous result, comparison with, so we take the initial condition from the experimental data. So we take this as an initial condition, and then we simulate, and we change the parameter to match the experiment, and then we overlap. So this is the experiment, and those are numerical simulation. But we got a problem. Okay. Okay. Because the ultimate goal is to simulate the tumor. Okay, so it's collection of the cell. Okay, so we will model the cell adhesion also. It's a fully 3D simulation. But using the axis symmetry, all you can do is they separate this aligned this way, right? Because we assume the axis symmetry. So we cannot simulate the tissue, like tumor tissue. Just like here. Okay? Your cell division is like aligned like vertically. So that's why we move to the fully 3D simulation. So to extend the 3D immersed boundary, we have to solve a couple of difficulties. First of all, define the cell division force direction. Well, in 2 dimension, we have very simple the direction, but in 3D, we have many directions. Okay, and then the mass conservation, well, which means initially we have the cell, single cell is double the mass. Once we double the mass, and before the cell division, the more like the mass is conserved. Okay? So we have to conserve the mass, and then there are some numerical difficulties. Okay? So mass regenerations. In axisymmetric case, okay, so without the interpolation, we have some problems. Okay, so this is the magnification. So because when cell is contract, the interface cell membrane is increased. Okay? So we have more mesh. So in that case, we adaptively adding or subtracting. Okay? So but that is very simple because we can approximate the quadratic interpolation. We add and delete. It's very simple. But however, in the 3D, it's not that simple. So this is 3D extension. The mathematical model is more like similar, but the numerical treatment is very difficult. Well, first of all, the mass conservation in the immersed boundary. So we exactly mass conserve. Okay? So we calculate the numerical mass, and then we correct the mass. So about this mass correction in the immersed boundary muscle, we published 2 papers in 2 dimension and 3 dimension for a 2-phase fluid flow. Okay, so this is the illustration of the mass conservation, the volume correction. Okay, so we put the drop and apply the shear flow, and then during the computation, the mass is shrink. Okay, the mass we lost the mass. Okay. But however, if we use the mass correction, we can preserve the mass. Okay. Once you lose the volume, we have the overestimate the curvature, and then the surface tension is the higher, so it's getting worse. Eventually it's disappear. Okay. So this is not good. Okay. So the volume correction is basically you calculate the normal direction of the surface, and then by the increase or decrease, so we adjust the volume. But here is the one problem again. We correct the mass. However, the mesh quality is not good. Okay? Mesh quality is not good. Okay? So some is distorted a lot. Okay? That will spoil the computation, the long-time computation. So we have to solve that too. Okay, so this is the illustration of the mass, the surface point. Okay, this is not uniform, and then we apply the remeshing, the algorithm. Okay. So initially this non-uniform distribution of the surface point, and then we redistribute and keep the original shape. So before the remeshing, so we have the non-uniform mesh quality. So after we apply, so we have good mesh quality. Okay, so we apply 2 techniques. One is the volume correction. The other one is remeshing. Okay, using this, and then this one is to change the connectivity of the mass, the grid system. Okay, so this triangle is not good. Okay. So for a numerical computation, it's more like the regular triangle is good. Okay? But it's distorted, so we reconnect the mesh connectivity. So this is the result, the three-dimensional result. The first, we increase the cell mass twice. Once that the cell mass is twice, we decide the contrast ring position, and then we act the contraction ring. So here, without the mesh regeneration, the mesh quality is not good. It's too much the distortion. Okay. And then those are the result from the effect of the ester center positions. So we put symmetrically. So we have the similar result to the X-symmetric case. Well, by the way, this is the 3D. So for a better visualization, we just cut the slice. We see the middle part. So the ester is 2 here, and then the result is different. And we expand to the different location of the esters. So those are the symmetry location is plus. Here is the square, and then the circle. So it's not a symmetric division. Okay, so for the conclusion is to the realistic computation or simulation. So we did a 3D immersed boundary method, and we solved 2 problems. One is the mass conservation, and the other one is the mesh quality, the remeshing algorithms. And then as a feature, so we will do the tissue simulations. So we repeat, and then we have to incorporate the cell adhesion also. All right, so I think it's done. Okay,